Hello, my name is Mariam Abu-Adas, and today I'll be discussing number fields. We begin with the motivation. We wish to use number fields in order to come up with finite extensions of rational numbers for any degree n. And even more important than that, we can come up with Galois finite extensions of rationals for any degree n. We begin with some definitions. A number field is essentially a finite degree extension of the rationals. So K is a number field if it's a field, it contains the rationals, and if it's a finite extension of Q. So some examples of number fields are the rationals themselves, and this is just a trivial extension, or Q adjoined I, and this is known as the Gaussian rationals. Q adjoined the square root of D, where D is square free. This is known as the quadratic field extension, or Q adjoined the nth root of unity, and that's the cyclotomic field. So these are all examples of extensions of Q that are finite. Not all extensions of Q, however, are number fields. For example, Q adjoined pi, because pi is a transcendental number, this extension is an infinite degree extension. And these two are also not examples of number fields because this isn't a finite extension and this one doesn't contain the rational numbers. So let's discuss some properties of number fields. We know that the rational numbers have characteristic of 0. We also know that if you consider an extension of something with characteristic 0, that extension must be separable. Since all our number fields are extension of Q, which has characteristic 0, all number fields must be separable. We also know from the primitive element theorem that if you have a finite extension that's separable, it must also be simple. And we just showed that number fields are all separable, hence number fields must also be simple. In order for a number field to be a Galois extension, it has to be both normal and separable. We showed that all number fields are separable, so the only thing we have to show in order to show it's Galois is to show that it's normal. And number fields are not always normal, so they're not always Galois. So some examples of number fields that are Galois are Q adjoined I, for example, because it's the splitting field of x squared plus 1. So it must be normal, and we showed it's separable, so it's Galois. Another example is Q adjoined root 2, and that's the splitting field of x squared minus 2, for example. An example of a number field that's not normal and hence not Galois is Q adjoined the cubed root of 2. And it's not normal because we showed in class that the root of the minimal polynomial for this thing, which is x cubed minus 2, has roots that use the third root of unity, which are not in this extension. So some important theorems. Given a number field L, there's only finitely many subfields K, such that K is between L and our rationals Q. And the proof of this is quite straightforward. We have a proposition that says that if you have a finite extension that's simple, it's simple if and only if there are a finite number of subfields. And so we showed earlier that all number fields are simple, and since number fields are finite extensions, that means that there's a finite number of subfields K between Q and L. Now we talk about the motivation for using number fields, which is to show that we can find a number field with any degree n. And so the proof of this is to consider a specific type of number field, which is Q adjoined the nth root of 2. We claim that this has a minimal polynomial of x to the n minus 2, and that this is the minimal polynomial. We show it's the minimal polynomial by showing it's irreducible over the rationals. And to do that, we use both Gauss's lemma and Eisenstein's criterion. To use Gauss's lemma, we basically show that if we show that it's irreducible in the integers, then it must also be irreducible in Q. And so if we consider x to the n minus 2 in Z, we can use Eisenstein's criterion to say that if you consider the prime ideal 2Z, then all the terms, except for the first one, which is just 2, is in 2Z, but is not in 2Z squared, because 4 does not divide 2. And so this is irreducible in Z, and then by Gauss's lemma, it must also be irreducible in Q. And so since the nth root of 2 is a root of this polynomial, which we showed is irreducible, then this must be the minimal polynomial. And we know that the degree of an extension is equal to the degree of its minimal polynomial, and hence this extension, q adjoined the nth root of 2, must have degree n. Now we show that we can find Galois extensions that have degree n. So the issue with what we did previously is that these are not necessarily Galois extensions. We showed that the third root of 2, for example, does not allow this to be normal, so it's not a Galois extension. So this just showed that we have number fields of degree n, but now we want to show that we can find Galois number fields of degree n. And the idea for this proof is to consider q adjoined roots of unity. So we know from a homework, if you have q adjoined the nth root of unity, that has a Galois group that's isomorphic to z mod and the units of z mod nz. And so if we let n be p to the r plus 1 for p a prime, then this has a Galois group isomorphic to the units of z mod p to the r plus 1 z. To see how many elements this group has, we use the phi function and say phi of p to the r plus 1, and we find that that's equal to p to the r times p minus 1. And so we can write this as the cross of z mod p minus 1z and p z mod p to the rz, as this has p minus 1 times p to the r elements. And so if we consider the correlation between Galois groups and their fields, that implies that q adjoined zeta of p to the r plus 1 can be written as the compositum of the fields with this Galois group and this Galois group. And we know that q adjoined the pth root of unity for p a prime has Galois group as a cyclic Galois group with p minus 1 elements. And we can always find a Galois extension with a prime to with a degree of a prime to a power. So we denote c to the p r is as a Galois extension with a Galois group isomorphic to z mod p to the rz. And the idea is to find to do the compositum of these c's, c sub p, c sub some prime to some power, and since n can be written as the product of p sub i's to r sub i's, you can find the compositum of all of those, and that will give you a Galois extension of any degree n. So that's the general idea for how we would go about this. Some other places where number fields may be used is for Fermat's last theorem, for example, and this isn't necessarily correlated to what we were discussing earlier, but it's just some extra extensions of what you can do with number fields is use the proof for Fermat's last theorem. So number fields are all something called Dedekind domains, which are basically domains where your ideals can factor into prime ideals. And if we concern ourselves with whether or not these number fields have unique factorization, whether their ideals factor uniquely, then if we determine whether the factorization is unique, we can determine something called a class number formula, and this is an integral part of solving Fermat's last theorem. Thank you.